All right, guys, so let's pick up right where we left off and jump right into example 2. We had just derived the flexure formula, and now we are going to solve for the internal moment at this section shown using two methods. Okay, we're going to use the method that we just kind of derived, the flexure formula, so sigma equals MC over I, or this is sigma max. And we're also going to find the resultant by using basic principles, okay, which is basically statics and what we already know. Okay, so first part A here, sigma max equals internal moment C over I. We're looking to find internal moment. That's our unknown. So all we have to really do is define sigma max C and I. So C here, we know that C, whenever the formula is in this form, not my over I, C is just this max distance from the neutral axis to the most outer surface, and that's 6 inches. Okay, and our sigma max is the value of sigma at that point. So if we come back to this point, what's the value of sigma here? It's given us 2 ksi. Okay, and the neutral axis, just to remember, that's the point, that's the whole axis of zero stress. And moment of inertia for a rectangular cross section like the one shown, 1/12 bh cubed. Okay, so my base is going to be the 6 inches, my whole height 12 inches, and I just plug everything in, and I get 6 times 12 cubed for a grand total of 864 inches to the fourth. And I just plug and chug, and I get sigma max equals 1/12, equals m times 6 inches over 864 inches to the fourth, and sigma max is 2 ksi. So I can solve, and I get 288 kip inches. Done. One way done. Okay. Let's now talk about the other way of doing things. Part B. So let's remember, before we get to tackling this, let's remember from statics. When I have a triangular load distribution that looks like this, how do I find the resultant of this triangular load distribution? This resultant here. Let's say this is W and this length is some length L. All I have to do to find this resultant force F is say that that's just 1/2 WL, the area. Right? This is for a 2D system. But here you can see we're dealing with a 3D system. So area is in 2D as volume is in 3D. So for this, to get the resultant force, basically the axe here and axe here, I need to get the volume of what's happening. And it makes sense because here I'm given 2 ksi, and ksi is kips per inch squared. So I need to multiply it by inch, multiply it by inch to get it out of that. Okay, so to get it basically into units of force. You see? So I need to take force equals the 2 kips per inch squared times the 6 inches times the other 6 inches, and this is a triangle, so I need to multiply by 1/2, and I get my force, and this is the force of the couple here, this F. And then all I need to do is figure out the distance, this arm, because we know that M, the internal moment, is just F times the arm. So what's the arm? Well, again, come back to this drawing here. To figure out the distance that this acts from here for a triangular distributed load is just 1/3 L, or from here to here is 2/3 L. So same thing here. I can't really draw it on here. It's kind of confusing. Let me see. Here to here would be that 1/3, and here to the neutral axis would be that 2/3. And then here, again, we'd have another 2/3. So the total would be 2/3 of 6 plus 2/3 of 6, which is 8 inches, okay? So here, our moment is 36 kips times 8 inches, and we get 288 kip inches. Same answer, okay? And here, I have a picture down here that shows you a much better representation of what I could have drawn. Here is our couple. Here is the arm that it acts away from the NA, the neutral axis for both. And of course we need to add up this whole arm times the force to get the moment. Okay. All right, let's move on. Try another example here. Excuse me. Okay. Let's move on, try another example. All right, so simply supported beam has a cross-sectional area shown. Determine the absolute maximum bending stress in the beam and draw the stress distribution. We're not going to actually draw the stress distribution because I don't even want to attempt to draw this 3D drawing. So I already drew it I didn't draw it for you, but I copied it from the book. So we're just actually going to do the first part. Determine the absolute maximum bending stress. So that's what we want. Okay, to get sigma max, we need M max C over I, right? And we know how to get moment from here. So this is a simply supported beam. It's symmetrical. If this is my resultant, right, 5 times 6, 30 kilonewtons, that means that I have a 15 kilonewton force here, 15 kilonewton reaction here, up 15, negative 15, connect the two. Shear in kilonewtons looks like this. And I can easily get the moment now. Starting at 0, ending at 0. This is. Okay. And to determine what this shape is going to be, this is a straight line. Which means M is a parabola. And at this point, I need to have a slope of 0. At this point, it's 15, negative 15. I start with a slope of positive 15. I have a slope of 0. End with a slope of negative 15 for something like this. And if I want the value here, I just take the area under the curve. This is 3 meters. And I get 22.5. And this is my M max. Okay. It's my internal moment at 3 meters on the beam with the cross section shown here. Okay, so let's keep going. Now, this is a little bit new. I'm going to have to find the moment of inertia of this shape over here. So let me copy this. Actually, hold on, let's copy this down here and let's kind of make it a little bit bigger. Okay, so the way that this works, we can use a couple of different methods to calculate moment of inertia of these types of shapes. So some things we know, Some things we know. We know that moment of inertia for a rectangular section equals 1/12 BH cubed. And that's a really easy formula to memorize because I don't want to have to memorize a bunch of different types of moment of inertia formulas or derive them from dx, dy integrals or do any of those things. So I want to kind of stick to this if I can use it. And I can because all I have here really are just 3 sections. This would be like 1, and then another section 2, and another section 3 that are all rectangles. But the trick about moment of inertia is this is moment of inertia of a rectangular section that passes through the NA. But you can see here that only section 2, I'm going to put it in red, only this section passes through the NA. So this formula is only really valid for this section in red. For the other 2 sections in dark gray, I can use the same formula, but I have to now use the formula plus kind of a trick. So I have to say this, I'm going to call this I bar. For section 1 and 2, I would be I bar 1/12 BH cubed of that section plus the area of that section times d squared. And what is D? D is the distance from the center of that section to the NA. So let's write all this out, and I think it'll be a little bit easier to understand where we're coming with all these numbers. And I'll show you another really easy way to do it, and you can pick which one you like better. And I kind of just switch between both of them. Okay, so this, by the way, this is called right here the parallel axis theorem. And it means I want to get moment of inertia through an axis that's parallel to my neutral axis. So you can see this is parallel to this. That's why it's called the parallel axis theorem. It's a really easy way to get moment of inertia about any object from a different point, for an object that doesn't pass through the moment of inertia, through the neutral axis. Okay, so moment of inertia is equal to, now we're going to do the 1/12 times 0.02 times 0.3 cubed. And this is the red section. This is what we called section, I'm going to label it a little bit better here, section 2. Okay, that one's done. We're all good. It passes through the neutral axis, so no change. But now we need to add the moment of inertia of the other two shapes. So section 1 is going to be 1/12. I'm going to put it in big brackets, times B of that section, which is 0.25, this 250 millimeters, or right here, same up here, right? Times H 0.02 cubed. Now I need, oops, that's not a cube symbol. This is the cube symbol. Now I need to add the area, 0.25 times 0.02 times that D value. And let's kind of zoom in here to figure out what that D value is. Where did I go? I kind of clear this up a little bit so I can show you. So this D value is calculated as such. This line represents the center of that object. This is the neutral axis of the whole object where I calculated my moment of inertia about. And this is D. So this from here to here is I'll show you here, is 20/2, so 10 millimeters. This is 150, so D from here to here is equal to 160 millimeters. Okay, pretty simple. So here I'm going to come and put in 160 millimeters or 0.16 meters, and then I'm just squaring that. Okay, and I'm going to do, this is all for section 1. But you can see it's symmetric, and section 2 is going to have the same area and the same D, so all I have to do is multiply this by 2. And that's for section 1 and 3. And that whole long formula is my moment of inertia. And if I solve all of this, I get 301.3 times 10 to the -6 meters to the 4th. Okay. Now I'm ready to plug in sigma max as MC/I. And I'm going to plug in 22.5 times 10 to the 3 Newton meters times 0.170 meters divided by 301.3 times 10 to the -6 meters to the 4th. And I get a grand total sigma max of 12.7 megapascals. And you can see that right here. That's the very top value of my stress distribution and what we were looking for. We're looking for that sigma max. Okay. Okay, let's move on to another example here. This one's a fun one. Okay, so we have two designs, two potential beam designs, okay? And we want to figure out which one can support a moment, an internal moment value of 100, oops, I didn't circle the whole thing, of 150 kilonewton meters with the least amount of bending stress. Okay, and we want to know what that sigma value is. So you can see here the difference between these sections. One has double web, one has double flanges. Okay, so just from just from what we know about bending stress, it might be a good idea for you to think about this and take an educated guess as to which one of these you think is going to be able to take the highest bending stress. And I'll help you I'll walk you through this. So we know the max bending stress, the max stress occurs at the point farthest from the neutral axis. Okay, and what is the point farthest from the neutral axis? It's up here. So if I have sigma max here, it might be a better idea to double up the area here as opposed to double up the area here. Okay, so let's see if that's correct. I'm guessing B, right? Okay. So section A, let's start with section A. The first thing we want to do, let's find the moment of inertia of section A. And I'm going to do this a little bit of a different way. I'm going to erase this stuff so I can show you the alternate way of calculating moment of inertia in case you did not like parallel axis theorem. Okay. What we do is we can say, I'm going to take the whole moment of inertia of this block, but then I'm going to minus the moment of inertia of this and of this section, and I will get my answer that way. Okay, so I can say that I is equal to 1/12 times 0.2, which is the whole base of the flange, 0.2, times 0.33, the total height of the system. But now minus, right, that interior portion. And so that base is going to be and I'm just going to add it into one whole portion instead of splitting it up, the 1.7 times 0.3 cubed. And I get 0.21645 times 10 to the negative 3. And if you want to check this, you can do parallel axis theorem to kind of check this, okay? And then we can say sigma max is, we have the moment of 150. And I'm plugging in the moment of inertia. And I get 114.3 megapascals. And that's sigma max for section A. And we can do the same analysis for section B. Moment of inertia is that 1/12 times 0.2 times 0.36 cubed minus 1/12 times 0.185 times 0.3 cubed, and we get a value of 0.36135 times 10 to the negative 3 meters to the fourth. And we can now plug in our sigma max here, and we have the same moment times a C value. It's a little bit different based on geometry. And we get 74.72. So our assessment was accurate. B is the better candidate here because we can take same amount of moment with much less stress. So sigma max B equals 74.72 megapascals, and our answer is section B. Okay. All right, let's move on. So we're going to talk about unsymmetric bending. I'm actually going to leave these slides for summary slides for you and kind of just work in this empty space, okay, to derive what's happening here and to explain unsymmetric bending. We're going to go over unsymmetric bending and biaxial bending, do a couple of examples, and then we'll kind of move on from the bending topic and start some other stuff, okay? We'll go into transverse shear after this. So let's first talk about unsymmetric bending. Okay, and if we remember, we derived the flexure formula. We derived sigma equals negative my over I for transversely loaded beam. Okay, so what that means is if I have this cross section here and this is my neutral axis, I have some moment applied here and I have some B base here, some H here, and I can determine the stress caused by bending moment at this cross section. Okay, and I can determine the stress profile to look something like this. I know that here I have the sigma max in compression, and I have some other sigma here in tension, and I know this is my y equals 0, and I can also determine basically the stress at any point. Okay, I have one axis of symmetry here, and my loading and bending are happening in the same plane, right? I don't have any biaxial bending. Okay, what happens when I have other conditions? How do I calculate sigma basically? What if my cross section is not symmetric like this? What if when I fold it over, it's not the same shape? Okay, so what happens when I have an asymmetrical cross section? Can I still solve for sigma? And the answer is yes. Okay, also what if I have out of plane bending? Okay, so what we want to do is basically, let's think about an asymmetrical cross section and what that kind of looks like, what that would look like. So I'm going to draw this kind of potato shape over here. Okay, and I'm going to say that this has some center, some geometric center here, and that this is my y-axis, and that this is my z-axis, and that my moment here, this is my moment, right, applied about my z-axis. Remember, this is moment. I just can't draw it really in the, this is 2D, so that's why I'm using the arrows here, okay? So moment is applied about z-axis. Z-axis is my neutral axis, right? And we still have compression above and tension below, and stress at Z is 0. We still have all of those elements to be true, okay? So let's kind of draw what would happen here in terms of stress. Okay, I'm going to actually move this information so I can draw the stress profile. Okay, so let's kind of come here and see what happens with our stress profile here. Okay, and our neutral axis again is this z-axis right here. Neutral axis, and we know we have compression at the top. We have some sigma max here. And we have tension at the bottom. Okay, and let's say we define again our y value would be any point we want to find some sigma at, and then of course we also have our c value, which is the max distance from our neutral axis to the outer plane, okay, or the outer surface. And we can again isolate some small area called dA that acts some value z away and has some coordinate y, okay? And we know the flexure formula is based on equilibrium, right? So sum of forces in the x, it's a 2D image, this would be out of the page, coming in your direction, those would equal 0. And I also know that all compression needs to equal all tension. So anything here above the neutral axis has to equal right? It has to equal everything else. So that means this, if I take this integral, negative sigma dA for every single area equals 0, this has to be, this basically was what we said had to be true. And previously, for this to be true, so I'm going to write this out because this is super important. Previously, for this to be true, the geometric centroid must have passed through the NA. Okay? And so what we did, right, we would take moment about the z-axis, take moment about the z-axis, and I would get basically sum of mz. We'll say this direction is positive, and that has to be equal to m. The integral of y sigma dA has to be equal to m. And I got that sigma over y equals sigma max over c. And I could solve here and get negative sigma max, take this out. This is all from before, right? Then just recapping what we did before, okay? But now we want to check, what about moment about the y-axis? Because now we have this moment arm. We're taking this little differential element. So this is moment about the z-axis. What about sum of moment about the y-axis? Okay, we have no moment applied in the y. This is uniaxial bending, right? Single axis bending. Okay, so here, what's our moment arm? It would be z. And we would have sigma max over c, integral of y z dA equals 0. And this is a product of inertia now. This is not just moment of inertia. We call this the product of inertia. Okay, and this is I, Y, Z, and this will be 0 as long as Y and Z axes we choose are along the principal axes of inertia. I'm going to write that down and circle it. Okay, this is very important. So, for this to be 0, Y and Z axes we choose must be along the principal axes of inertia. And we call these our major and minor principal axes. And basically that's the maximum and minimum moment of inertia for a cross section. We need to choose those so that the maximum and minimum moment of inertia for a cross section are the Y and the Z, and we call these I major and I minor. Okay, sometimes these can be really hard to figure out, and we need transformation equations and sines and cosines and more circle and all this crazy stuff. But for us as civil engineers, we have some easy ways of identifying these axes because we don't get too crazy with our cross sections. So we're going to kind of stick to those easy ones in this class, okay? And here, we're going to stick to problems that at least have one axis of symmetry. So for example, a T section has at least this one axis of symmetry, okay? Or a channel section has at least this one axis of symmetry, okay? So here, this is a rule. So for us, the principal axes are always parallel. Sorry, parallel and perpendicular. So parallel and perpendicular to the axis of symmetry. So one is parallel, one is perpendicular. And this is only true if there is an axis of symmetry, which we're going to be sticking to shapes where there is. Okay, so I'll show you a couple of examples on this. If we had something that looked like this, okay, this would basically be my z, the axis where I'm bending occurs, and this perpendicular axis is going to be my y, and our IZ, right, is our I major, our IY is our I minor here. We can do the same thing for something that looks like this, although we're not going to necessarily get into shapes as complicated again, but our axis of symmetry here would be here. So this would be my z, and then all I need to do is go perpendicular to that at the centroid. This would be my y, and again, this y here is the I minor, and this is the I major. Okay? So basically the main idea here, as long as IYZ is 0, our equilibrium equations are satisfied for any arbitrary shape, so we're good. And as long as the moment is applied about Z, which is always my principal axis, okay, then we can use that linear stress variation and we're good. And we always want to choose our major axis, where moment is applied. That's why this is our major axis, okay? So with that discussion, we're going to move on now to biaxial bending, okay? We're going to talk about what happens when we arbitrarily apply moment, okay? What happens then if we're not just applying moment about one cross-section, but it affects both cross-sections. And this could happen, and it happens often actually, in a specific case of members, which are columns. Columns often experience biaxial bending, okay? And what we want to do is we also here want to define z-axis again as our maximum or principal axis, generally, okay? So let's have a couple of pictures here to demonstrate what's happening. This is our rectangular cross-section, and if this is my center, this is the y, and this is the z, what I'm saying is that my moment is applied here at some angle theta. Okay, and I can actually say now this is just equal to a complete component mz plus a complete component on the my, right? So this is 1 and 2. And my mz is just m cosine theta. My my is m sine theta. And we know that bending moment causes normal stress. So for 1 here, I would have sigma equals mzy over iz. This is negative. And here I'd have sigma equals myz over iy. Okay. This is negative because it's the left. This is positive because it's up. And then here, same as before, I'm going to add the two. And I get sigma equals negative mzy over iz, moment of inertia about the z, plus myz over iy. And this is basically like negative times a negative here, so it becomes a positive, and that's why we're adding here, okay? And this is the biaxial bending formula. Okay. So let's now talk about the neutral axis orientation. How do we find where the neutral axis is here? And we can find the neutral axis. I'm going to put this neutral axis orientation. So we can find by setting sigma equal to 0 here. So we have 0 equals negative mzy over iz plus myz over iy. I'm going to highlight this equation because it's really important. So just so we remember this formula. This is biaxial bending. Okay. And we can plug in what we know here. We have m cosine theta y plus, or actually it's negative. We're going to actually set them equal to each other. We'll put one on each side. Equals m sine theta z over iy iz. You can see here that m's cancel out. And if we simplify all this, we get y over z equals sine theta over cos theta times iz over iy. And if we keep simplifying, we can call this quantity, right, y over z, some tangent alpha. This here is tangent theta. And we get this function that's tangent alpha equals tangent theta times iz over iy. It's a function of those moment of inertias. And alpha is equal to the orientation of my neutral axis. So let me draw that for you. This is my m. And some theta would be this here. And my alpha, where is my alpha? I'll do pink. My alpha is some, let me try to get this to go through this point. Some neutral axis orientation here. And this is my alpha. Okay, and my max stress at furthest distance from NA. Okay, and alpha always measured, alpha is always measured from Z to Y direction.